Pi, the only time I have seen it in high school being used for not pi is as a variable for permutation, which I doubt you've come across yet.
Why
Outside of that, you can pretty much assume it's pi. Huh?
capital Pi for multiplication?
Oh, true. For product. Yeah, maybe I should say that. Maybe it does come up in other ways and I just don't remember. Okay, so let's recap the big one from last time. You guys already briefly mentioned it. Ohm's law, that was one of our big ones from last time. What does Ohm's law say?
Voltage equals current times resistance.
Perfect. And that is our way of calculating the voltage, the difference in potential, the voltage across some resistor. Right? Now, what's the other major circuit component we've been talking a lot about?
Capacitors.
Capacitors. How do we get the potential difference across a capacitor? So let's remind ourselves, what's the definition of capacitance? Remember what capacitance is?
It's a measure of the charge they come.
It's the charge per something.
Unit area. Oh.
Now, because the area increases the capacitance. It's the charge per volt. That's exactly what it is. It's the charge per unit volt. It tells you how much charge you'll get on those plates per volt that you stick it in the circuit. You always know, I shouldn't say always, but you'll typically know the voltage of the circuit that you're working with. And so, how do we get the voltage then across the capacitor?
You just move you divide by C and move V over.
Right, just multiply both sides by V and divide both sides by C, or in other words, you get V is equal to Q over C. So here's how we're going to be calculating voltage across a resistor. Here's how we're going to be calculating voltage across a capacitor. So that's what I have written right here. Doing those two things, here's our voltage across a resistor. That's just Ohm's law. That's our voltage across a capacitor. Going to qualify this one more time, and then we'll forget about it going forward. Ohm's law only really applies if the resistance of your material isn't changing much with the temperature. So it's a pretty good approximate for metals close to room temperatures. That's where it works. When we're talking about things like semiconductors, so like silicon, you know that you use silicon a lot in chips. You probably heard that Silicon Valley. Why is it called Silicon Valley? Well, because they were actually mining silicon there for their chips. It's used a lot as a semiconductor. It does not follow Ohm's law. So this Ohm's law does not apply to everything. It applies to metals, the things we're typically using as conductors, close to the temperatures we're talking about. So from here on out, we'll assume it always works, unless otherwise specified. On the other hand, capacitance is capacitance. It's a property of the actual thing itself. And so this in no way depends on these other things. So that's a more permanent thing. Okay. So with that qualifier out of the way, let's already redo something that we did before, because I need you to start seeing the parallels between capacitors and resistors and why these two things, in a sense, go hand in hand. So, already did this derivation, but let's do it again. So we're going to look at capacitors in series. So here I've got my circuit. I've got some battery hooked up. Remember, that's our symbol for a battery, a small line with a taller line. The plus means that this is a positive terminal, that's a negative terminal, and the battery has some voltage V. It could be like a 12-volt battery or whatever. Okay, so we got a battery hooked up to the circuit. The circuit has two capacitors. This is just point A, B, and C somewhere in the circuit. What we were looking for is, I want to come up with a circuit that is completely equivalent to this, that only uses one capacitor. So what capacitance do I need this capacitor to have so that it functions equivalent to both these capacitors? In other words, what capacitance should this have so that it stores the same amount of charge per volt? With me?
Yeah.
Okay, so that was a problem we were working on. And this in series just means that they're both lined up along the same conducting path. Okay, so first off, we're assuming identical batteries in both these circuits. We're trying to figure out what capacitor I should use here to create a circuit that's logically equivalent to this one that has two capacitors. That's our problem. Now, the voltage across this battery is going to be equal to the voltage from A to B plus the voltage from B to C.
Right.
That's the total voltage from the start of the battery to the end of the battery across the entire battery. That's V. So V is equal to the voltage from A to B plus the voltage from B to C. You follow that? And now, what is our voltage from A to B? What is our voltage across a capacitor? Our voltage across a capacitor is just the charge divided by the capacitance. So this is just equal to the charge we get on there divided by its capacitance. And the voltage from here to here is just equal to the charge on that capacitor divided by its capacitance.
The charge is the same, right?
How do we know that the charge on both these capacitors are the exact same? So imagine it's when I first plug my battery in. And let's think about the actual electrons. So I first put my battery in. What's going to happen is an electron is going to start flowing out this end, and it's going to come all the way to this plate.
Yeah.
And so this plate is going to get a little bit of a negative charge. That little bit of negative charge is going to push an electron off of this plate. And so an electron is going to travel off of this plate up to this plate, making a negative charge there. But since this plate lost an electron, now it has a little bit of a positive charge. And the electron up here now pushes the electron off of this plate, which then goes into the positive end of the terminal of the battery, leaving a positive charge there. So one electron on this plate shoves one electron off this plate, shoves one electron on this plate, shoves one electron off this plate. And so all the plates have the exact same charge, just different signs, but same charge, same magnitude charge. So whatever the charge is Q on this capacitor will always be the exact same as the charge on this capacitor. Because the only way this plate gains electrons is if this plate loses electrons. That make sense?
Yep.
Okay, so that's why those Q's have to be the same. So I know that my voltage, since it's the voltage across both those capacitors, my total voltage from my battery has to be equal to Q over C1 plus Q over C2. Now I'm using the exact same battery over here, so the exact same voltage.
Yep.
We're saying we're looking for equivalent capacitance, so it's going to get the exact same charge on it. So what does this C have to be?
2.
Well, we'll just plug in. So our voltage is equal to Q over C1 plus Q over C2. And that same exact voltage is equal to Q over C, the C that we're looking for.
Yeah.
So now we go ahead and plug that in on either side of our equation. In other words, these two things have to be equal to each other.
Right.
And now divide both sides by Q, and we get this. And so 1 over the capacitance we're looking for is equal to 1 over C1 plus 1 over C2. If we had 3 capacitors in series, that would be plus 1 over C3, etc. And so yeah, in the concrete case here, if this capacitor was exactly 6 microfarads, and if this capacitor was exactly 3 microfarads, then 1/6 plus 1/3 is 1/2. So the equivalent here would be 2 microfarads. In that concrete case. But here's what it is in general.
Yeah.
Okay. Repeat, but this time now just with resistors. So, same exact problem, but rip out those capacitors, shove resistors in. There we go. I've got my circuit here, some battery with some voltage. I'm looking for the equivalent circuit with the equivalent resistor. Good?
Yep.
Now we set up this problem identical. The voltage, V, is going to be the voltage from A to B plus the voltage from B to C. What's the voltage across the capacitor? We use Ohm's law. The voltage across this capacitor
Resistor.
is whatever the current is times R1. And the voltage across this capacitor is whatever the current is times R2. How do I know that these have the same current? Conservation of charge, right? You're making a face like a duh. It's the most obvious thing ever. Whatever current flows through here flows through there.
Right.
We're not producing current in the middle of this thing somehow or somehow eating it up. So the same exact current flows all the way through the circuit. Now we are looking for an equivalent resistor here. So that means we're looking for the R that gives us the exact same V and the exact same I. The same voltage, the same current, same resistance. Okay. Now, in the concrete case where this is 6 ohms and this is 3 ohms, does adding a resistor help current flow or does it block current from flowing? It's going to block current from flowing. So do we expect this R to be bigger or smaller than these R's? Bigger. We're going to have to put a bigger resistance in here to function the same as these. Capacitors are the more unintuitive one. You would not have guessed from the beginning that to get equivalent capacitors, oh yes, use smaller than either of them. This one pretty much appeals to the intuition. And you'll see that's the way it comes out. So our voltage is equal to I times R1 plus I times R2, and our voltage is equal to I times R. So these two are equal to each other. divide both sides by R. And so our equivalent resistor is just equal to R1 plus R2.
Yeah.
So this one's 6 ohms and this one's 3 ohms. To get the equivalent one, it's just 9 ohms, which you probably would have guessed. Okay, and in general, what if we had n resistors in a row? Then the equivalent resistor is just the sum of all the resistors. Good? Pretty straightforward? Okay, now in parallel, let's go back and do something that we already did. So now I've got my battery here, and I've got 2 capacitors now in parallel. Now, are they going to have the same charge on them?
Yes.
No, not necessarily this time. Remember, capacitance is charge per volt. What's going to be the same for both these capacitors? The voltage across them is going to be the same.
Oh, but the capacitance is different.
But the charge that each one has is going to be different because the capacitance is going to be different.
Yeah.
So different capacitance, different charge, because they're going to have the exact same voltage across them.
Right. Okay.
Because remember, how much does my voltage change if I go from right here to right here?
Nothing.
Nothing. So the voltage from here to here is the same as the voltage from here to here. So same voltage across them, which is going to be just the voltage of our battery.
Yeah.
So our voltage of our battery is going to be the same as the voltage across here. So the voltage across our first capacitor is whatever the charge is on it divided by its capacitance. And the voltage across here is also going to be whatever the charge is on it divided by its capacitance. Now we are looking for a circuit with an equivalent capacitor. Now this one's more intuitive with our intuition. If my capacitor is going to be equivalent to these 2 capacitors, then how much charge does it have to store for the same amount of volt?
Now my
The sum of them?
The sum of those 2.
Here's what I found.
Thanks. But anyways, so the voltage here is going to be whatever charge this one stores divided by its capacitance, if it's an equivalent capacitor. But our charge on this one has to be equal to the sum of the charges on these 2. That's what it means for it to be an equivalent capacitor. It's getting the same charge per volt. Right?
Yep.
That's what equivalent means. However much charge this stores, if these 2 together are storing 1 coulomb per volt, then this one has to be storing 1 coulomb per volt. Okay, so that's the important link there, is that the charge on here has to be equal to the sum of the charges on these 2. And now we can use these 3 equations to substitute in. Take each of these equations and solve for Q1, Q2, and Q and plug them in. So Q, if we take this one and we solve for Q, just move the C over here. Q is just going to be equal to V times C. Q1 is just going to be equal to V times C1. And Q2 is just going to be equal to V times C2. You see that? So making those 3 substitutions. Q equal to Q1 plus Q2. Q equal to Q1 plus Q2. Now divide both sides by V because it's the same voltage across all these. And we get C is equal to C1 plus C2. Which we've already seen before. Good? Now, do the exact same thing. Once again, just replace your capacitors with resistors. And the logic for solving these things is almost identical. So once again, the voltage across R1 and the voltage across R2 are
Same.
the same. Just like the voltage across this and the voltage across this are the same. So we're looking for an equivalent resistor, so the voltage across this resistor is also going to be the same. What is the voltage across R1? Just using Ohm's law. It's whatever the current is times R1.
Yeah.
What is the voltage across R2? It's just whatever the current is times R2. Now how do I know that these 2 currents are actually the same?
The resistor divides the current, like it blocks it.
Yeah, it slows it down. So how do I know that the same amount of current goes through this resistor as through this resistor? How do I know I1 and I2 are actually the same?
The voltage across them is the same.
Because more voltage tries to get through R1, and then less voltage tries to get through R2.
The answer is they're not the same.
Oh.
Because Ohm's law, if the voltage is the same and the resistors are different, the resistance is different, the current has to be different. So they're not the same. Same reason that the charge wasn't necessarily the same on these. The current, not necessarily the same here. And once again, we have the current over here, whatever the current is, I going through here. Now, if we have an equivalent resistor, then that means it has the same voltage for the current. So the current here has to be the sum of these two currents here.
Yeah.
Just like the charge here had to be the sum of the charges here. It's what we mean by an equivalent capacitor. It's what we mean by an equivalent resistor. I'm just replacing Q's with I, basically, and then the logic's the exact same. With me? And then once again, we can use these three equations to solve for I, I1, and I2. So I is just equal to V over R. I1 is just equal to V over R1. And I2 is just equal to V over R2. Divide both sides by V, and there we go. So your equivalent resistor is equal to the sum of the reciprocals. Sorry, the reciprocal of your equivalent is equal to the sum of the reciprocals. But once again, this should be intuitive to you. If this one has a 6 ohm resistor and this one has a 3 ohm resistor, how would we expect their equivalent to behave? Bigger or smaller?
Smaller.
It has to be smaller. Why? Because now there's more paths for the electrons to flow through. There's more paths than if it was all forced to go through the 3 ohm resistor, and there's more paths than if it was forced to all go through the 6 ohm resistor. So whatever our equivalent one is, it has to be smaller than the 3, and it has to be smaller than the 6. So if you would have thought about it enough, you would have guessed that this had to be smaller than either of those two numbers. And it turns out it's going to be exactly 2, once again. So, summarizing these things. When we are talking about in series, if we're looking for the equivalent capacitor, here's how you solve it. If you're looking for the equivalent resistor, here's how you solve it. And if we're talking about in parallel, then do the reciprocal of them. And that's what we summarized so far. Those derivations, almost identical. And the thinking you use, almost identical. Good? I don't know why we start with capacitors. Resistors are easier to think about. But it's the way we go. Okay. So now, we're going to do a bunch of examples just working with circuits. So here we go. Here's some circuit. We've got, remember what that fancy E means?
Perpetuity.
Epsilon.
No, and no. This isn't this symbol.
Oh, sorry.
It's just meant to be a script E. That's all it's meant to be.
Oh.
What does it stand for? We only use it with batteries. I probably should have used it over here rather than these.
Internal, like what makes the...
Yeah, it's the electromotive force. And it's not a force. It's a potential. But, so, we use that E and we use it to symbolize the voltage across the battery. So this is an 18 volt battery is what that is saying. We'll always use little r's for the resistance inside of a battery, big R for an actual resistance of a resistor in the circuit. Good? So here's an 18 volt battery and its internal resistance negligible. Hooked up to the circuit has a 4 ohm resistor, 6 ohm resistor, 3 ohm resistor, and some current traveling through these things. Good so far?
Yep.
Our job is to find the amount of current going through each of these resistors and to find the equivalent resistor for this whole thing. Good? All right. What should we start with? Should we find the current first or the equivalent resistor?
Let's do current first.
If we do the equivalent resistor first, then we can use that to find the total current traveling right here.
Yeah, but then isn't each
It's
current-
not always going to be obvious which way you should go. So I may give you one where it's actually easier if you do the equivalent resistor first, and I may give you one where doing the equivalent resistor is a very stupid approach.
But isn't current different through each resistor anyways?
Yes, the current is going to be different through each resistor anyways.
So how would finding the equivalent resistor help with that?
Because then we can find I1.
Oh, we know that. Okay. Alright.
Okay, so let's start by finding the equivalent resistor. I can replace all three of these resistors with what? How do we do this? Well, let's start by collapsing these two that are in parallel. So, what is an equivalent resistor to these two?
9 ohms.
9 ohms, right?
No.
Yes.
It's the reciprocal.
Yes. 9 ohms.
It's the reciprocal.
So, here's where stopping and thinking about it rather than trying to remember your equation is going to help you. If the electrons have 2 paths, does that help more flow or less flow?
Less flow.
Less flow with 2 paths?
No, more flow.
More flow. Follow your intuition, not thinking towards the answer you think should be the right answer. Already your intuition is telling you more electrons should be able to flow than if it only could go through the 3 ohm resistor, or if it could only go through the 6 ohm resistor. So the equivalent to 2 in parallel better be smaller.
Right.
And so in this case, our equivalent one that we want, 1 over the R we're looking for, is going to be equal to 1/3 plus 1/6. And what's 1/3 plus 1/6? 1/2. So our equivalent R is 2. So these two are the same as just a 2 ohm resistor. So we could replace both those with just a 2 ohm resistor. And now we have a 4 and a 2 in series,
Which is 6.
which is a 6. Getting through a 4 and then a 2 is harder than just going straight through a 4 or just going straight through a 2. Is that not appealing to your intuition?
I have a slight question.
Go ahead.
If it's a resistor and it's in series, then wouldn't you add them together?
Yeah. So 2 plus 4 is?
I thought this was a series.
No. This is parallel. You can do both at the same time. Series is you have to do one, then the other. Okay, maybe you're getting confused because I'm not explaining what we did first. So first I said, let's look at these two in parallel. You see that an electron going from here to here has 2 options. So these are in parallel.
Oh, so it's based on the options.
That's one way to think about it. Parallel means multiple paths.
Okay.
Series means they're in the exact same path.
Oh, that makes a lot more sense.
Okay. So, having the option of going through a 3 or a 6 is equivalent to me forcing you to go through a 2. So get rid of those, and now forcing you to go through a 2 is the same as giving you an option of a 3 or 6.
Yeah.
Okay, so now I'm forcing you through a 4, and then I'm forcing you through a 2. That's equivalent to forcing you through a 6. So our equivalent resistance, our equivalent resistor that we were looking for, the R that we were actually looking for here, R is 6 ohms. So forget what we wrote up there. 6 ohms is our equivalent resistor. If we were to rip out all 3 of those resistors and just put in a 6 ohm resistor, that would be equivalent. So now, what is the total current flowing through this circuit?
Yeah, it's just your voltage over resistance. So it's 18 over 6.
Which is
3.
3 ohms. How's he getting that? Ohm's law. Your voltage, what's the voltage of our circuit? 18. Has to be equal to your current times your resistance. And all these resistors are logically equivalent to just a resistor of 6 ohms.
Oh.
That's why it was easier to first find the equivalent resistor and then try and figure out what the current is. This is for current I1, this outside current, not the inner side current, because it's like we ripped out those inner ones in our
Oh, yeah,
equation.
and to find the I, you just divide by 6 on both sides.
Right. So I1 is equal to 3 amps. So now we have that current.
Yeah.
Okay, so now let's go back to our initial circuit. So back to this. We know what I1 is. Now what is I2 and what's I3? How much of our current is going up here and how much is going down here? Now first off, I2 plus I3 has to be equal to 3 amps. What comes in is what's going out and around.
Doesn't some of the current get released as heat? Or am I getting something wrong?
None of the current gets released as heat. Energy gets released as heat.
So
We're not shooting off the electrons.
Oh.
We're just making things jiggle around more, which is ultimately emitting. You can think about it as like losing energy through coming into contact with like the air around it. That's one of the ways heat's being lost, just whatever.
Is I2 1.8?
Is I2 1.8? No. What is the voltage across this resistor?
It's the, what do you mean voltage?
How do you find the voltage across a resistor?
Oh, it's just a phone. It's resistance times the.
It's just resistance times current. So 6I2 is the voltage across here.
Yeah.
What's the voltage across here?
3I3.
3I3. And how do I know that those have to be equal to each other? Because the voltage from here to here is the voltage from here to here. It doesn't care what path you take.
Right.
Good? Now, you could have already guessed it. Look, if this one's twice as hard to go through as this one, then how much of the current is it going to get compared to this one? Half as much. So you should have already been able to guess 1 ohm up there, 1 amp here, 2 amps there.
Okay.
And it turns out that that's what this is going to say. Right? So what is this saying? This is saying that 2 I2s is equal to an I3. I3 is twice as big as I2.
Yeah.
And I know that I2 plus I3 has to be equal to 3 amps. You can solve those two equations simultaneously to get the 1 and the 2, or you can just instantly see it. So, I2 is going to be how many amps? 1 amp. And I3 is going to be
2 amps.
2 amps. And nothing surprising about those answers when you stop and think about it. Resistors pretty much appeal to your intuition when you stop and think about it. Capacitors, not so much. All right, any questions on that? Anything weird? Anything you want to explain better? We can take our times with these examples. Today's class, in terms of theory, is one of the easiest ones. We're mostly just going to be going over examples like this.
Is this just data chapter 4?
No, it's a long chapter, direct current circuits.
Oh, really?
Yeah.
This is the whole chapter?
And we're the end of my drawing there. The little battery at the bottom. Okay. So there's that circuit. Let's move on to another one. So we've got another circuit. What we have here is I've got an 8-volt battery, ignoring its internal resistance, and I've got 2 light bulbs, each that have a 2 amp, or each that have 2 ohms of resistance. So 2 little light bulbs. And in one scenario, I'm going to place those light bulbs in series, and another scenario, I'm going to place those light bulbs in parallel, in the exact same circuit. And what are we going to look at? We're going to look at the current in each of these cases, and we're going to look at the power outage of the actual light bulbs in each of these cases. Okay. Now, obviously, the power output should be the same in both cases since it's the same battery, right? I wouldn't say right unless it's wrong, right? Yeah, get to think about these. Try and develop some intuition for it. Does the same amount of current flow in both these cases? Which one has more current flowing? The bottom one. When you stop and think about it for a second, you think, a dot. Yeah. This one, you're forcing them all to go through both those resistors. Here, you're giving them an option. Here, it's easier than if you just had one light bulb to go through. Because now they have 2 options.
So the power is greater in the parallel.
So we're going to see more current here, and we're going to see much more power outage here. But let's start with the in-series one. Okay, so here we are. Here's our circuit. First off, how much current then is flowing through this circuit? What is I sub A? What is the current in scenario I sub A, because it's our current in scenario A?
4.
It's what?
4.
4?
Because it's 4, because
Should be 2 amps.
when the 2 resistors in series is equivalent to 1 4-ohm resistor.
Yeah.
That's one way you can think about it. So that's the equivalent to 1 4-ohm resistor.
But
And 4 times what gives you 8?
2.
2.
Oh, so it's 2.
So I sub A is going to be equal to 2 amps.
yeah.
Perfectly valid way of thinking about it. Now I'm going to give you another way of thinking about it, just to introduce Kirchhoff's rules before we say them. If I start right here on the circuit, and I go all the way back to where I started, what was my change in voltage?
0.
0. And so, I'm going to track my voltage as I go around here. Right?
Yeah.
So as I go through the battery, what happened to my voltage?
Nothing changed.
It increased.
It increased by 8. You have a change of 8 volts across the battery. That's what it means to be an 8-volt battery.
Yeah.
Okay, so we get 8 volts crossing the battery. Now I'm going to lose potential going across this resistor. So I'm in a minus 2 times I, whatever our current is. And then going across this resistor, I'm also going to minus 2 times I. And now I'm back to where I started. So that all has to be equal to 0. You with me?
Yeah.
And now you can see how you do this. Move those to the other side, you get 4I. And then divide both sides by 4 and you get I is equal to 2.
Okay.
So the way you thought about it, perfectly fine. But when you get to more complex circuits, this is a more natural approach because it's not going to be easy on how you go about reducing things. But perfectly fine to think about that way. The right way to do it with such a simple circuit, the way they wanted you to do it, but just want to show you that way of thinking. Okay. So we found that 2 amps. So now what is the power output of one of those light bulbs? If it has a resistance of 2. Remember power? It's written over there.
Oh, yeah.
Far right. One of the things we ended with last time. How do you get power?
Current times voltage.
Current times voltage is the most standard way it's written.
That makes sense.
We'll scribble that up here. Power, typically the way you find it is current times voltage, and you can use Ohm's law to get the other two ones written over there. You can also write it as I squared times R, or you can write it as V squared over R. That's just substituting using Ohm's law. But there's the most natural way. So what is the power output of this light bulb?
4.
4?
The current that goes through.
Wait.
What's
No, 8.
what's the potential across this?
16.
I'll tell you that. One of your answers was right. Okay. What is the potential difference across this resistor? What is the change in voltage across this resistor? Remember, 2 amps, and it's a 2 ohm resistor. So what's the voltage across this resistor?
8.
Ohm's law. We have it written here. Voltage is equal to current times resistance. It's a 2 ohm resistor with 2 amps of current. So the potential across here is
4.
4. There we go.
I said that earlier.
And so our power now, take your voltage and multiply it by I for your power.
8.
8. So this light bulb is giving off 8 watts, and this light bulb is giving off 8 watts. And so the total power output of this system, piece of A, is equal to 16 watts. Alright, now let's put the lights in parallel rather than in series. Same exact battery, just change the other configuration here. A 2 ohm resistor and a 2 ohm resistor in parallel, what's their equivalent resistor?
1 ohm.
Just 1 ohm. Because a half plus a half is 1. And the reciprocal of 1 is 1. So this is equivalent to a 1 ohm resistor. And so if I have an 8 volt battery with 1 ohm of resistance, then my current is going to be 8 amps. If my voltage is 8 and my resistance is 1, then my current has to be 8. Good. So now, what is the power output of this light bulb?
8.
16.
4.
Just throw numbers out there.
32.
Let's start by how much current is going through this wire?
Oh, it's 4 amps. Right.
4 amps is going through this wire, and 4 amps is going through that wire.
So
Sorry.
both light bulbs are powered by 4.
So 4 amps times 2
It's 8.
gives us 8, which is the voltage.
Yeah.
And now multiply by the current to get the power.
It's
64.
what? Oh, the current's 4, sorry.
8 times 4 is
32.
32. So now this is becoming a 32 watt light bulb. And this is a 32 watt light bulb. for now a total from both light bulbs of 64 watts. And so by putting them in parallel rather than in series, we increased our power output by 4. Which you could have pretty much guessed at, because the equivalent resistor here is 4, the equivalent resistor here is 1. So not completely surprising, but a little bit surprising that just changing that arrangement suddenly would make your light bulb 4 times as bright. Giving off power 4 times as fast is a better way to say it, because we perceive brightness weird.
Yeah.
But, there we go. Any questions on that example? I'll have to move you that, okay.
Wait, so why do they measure light bulbs in watts and not in ohms? Like when you buy a light bulb at the store.
Because they can already anticipate the circuit that it's going to be a part of. And what does a homeowner care about?
The brightness.
Yeah, it gives you a sense of how bright it's going to be, how much power it's going to give off.
Okay.
So, yeah, they can anticipate that based off of the current they know it's going into.
What's a unit for watts again?
Joules per second. Unit of energy per second is power. Power is energy per second.
Okay.
Okay, good? Okay, 2 rules that we've already been using. I have no clue why this guy Kirchhoff gets credit for the rules, but here's the 2 rules. Rule number 1, at any junction in a circuit, the sum of the current is 0. What is a junction? A junction is just a point like this, where you have 3 or more ways of feeding into it. This is not a junction, where you're just flowing through. This is not a junction, because you're just turning. This is a junction.
Why is the sum of the current 0?
What do we mean by the sum of the current is 0? What's coming in is going out. Nothing's sticking around.
Oh, I see.
That's all it's saying.
Okay.
Or in other words, charge is conserved.
Isn't that true over any closed section of the circuit?
Yeah, this is true at literally any point along it, but when we do our analysis of circuits, we mark the junctions and we apply this rule at each of the junctions.
But it applies to every point.
Yeah, right here. As much current as is flowing into that point is flowing out of that point.
So why is it necessary to specify the junction?
Because we only bother stating this at the junctions. When we do an analysis of a complex circuit, we only look at all the junctions and think about the current flowing into and out of each junction.
Oh, I see.
Basically, the junctions, if you were to think like graph theory-wise, act as the nodes.
The nodes.
This is just an edge
Okay.
to the battery. And it doesn't matter, that has a right turn in it.
Yeah.
Okay, so that's his first rule. At a junction, current that flows in is also current that has to flow out. None of it sticks around. So you use positive values for current coming in, negative current for current flowing out, and when you add up those currents, it comes out to 0. We already applied that when we were thinking about this point right here. We said current coming in is equal to 8 amps, current leaving is 4 and 4.
Yeah.
So if we were to add up current coming in, that was positive 8, and then current leaving was minus 4, and then that current leaving was minus 4, and that all equals 0. It's all same. So we already intuitively do this, but there we go, stay as a rule. The second one, again, one that we've already said a bunch of times, in a closed loop, in other words, if you come back to where you started, your change in potential is 0. The sum of all your potentials will come out 0. That's the second rule. And this is true for any conservative force. It's what it means to be a conservative force. Is if you end where you started, your change of potential energy was 0, and so obviously your change of potential was 0.
Right.
So 2 rules we've already been using, but there we go, got them stated. We can now call them Kirchhoff's rules to remind you about them. There they are. Good? Both those make pretty good sense?
Yep.
All right. So with that, let's jump into another circuit. Here I've got a battery. It's a 12-volt battery with an internal resistance of 2 ohms. So I drew it as a battery right next to a resistor. Here we have a 3 ohm resistor and a 7 ohm resistor. And then here we have another battery. This is a 4-volt battery with 4 ohms of resistance inside of it.
So that battery has a resistance of 2 ohms. Is that what you're saying?
This battery has a resistance of 4 ohms.
Yeah, okay.
This battery has a resistance of 2 ohms. I'm not sure which one you're talking about. Okay, so there's our circuit. Notice. Positive terminal, positive terminal. So which of these batteries are stronger?
The top one?
The top one's 12 volts, the bottom one's 4 volts.
Right.
So which way is current going to flow in the circuit?
Left or
Current's going to flow this way.
counterclockwise?
So our current is going this way.
That's so strange.
Remember, current is not the electrons. It's the positive.
Yeah, right.
Okay. Yeah, you got to pretend that electricity is really positive things moving around, not negative electrons.
So is that battery basically just one big resistor then? Because it's not actually adding to the flow, is it?
It's not adding to the flow, it's subtracting from the flow.
So it's like
And what we're actually setting up in the circuit here is recharging a battery. So you have to use one EMF to recharge another EMF, recharge another battery. So that's what the scenario is actually would be like if you're looking for a physical scenario, this could be representing recharging a battery. Good so far? Okay. So our job is to find the current, find the voltage from A to B, 2 random points in our circuit, and then find the power output for each of the batteries. Good with each of those? Okay. Now, how on earth are we going to start this process? We got to find the current. Right? So I'm going to start here at point A, and I'm going to go around the circuit back to point A, and my total change in voltage will be 0. Okay, so let's get going. First off, here I go. I'm from point A. I got to go through that resistor.
Yeah.
If I go through a resistor in the same direction as my current, am I gaining energy, gaining potential, or losing potential? Losing potential. So I just lost 2 times whatever my current is going through this resistor. Now I go through the battery. Do I gain or lose potential going through the battery? The EMF. I gain, and I'm going to gain 12 volts. Now I'm going to lose 3I traveling through here. Minus 3I. I'm finding the battery now. So I'm minus those 4 volts. Because the battery is 4 volts in that direction, I'm going this way around my circuit.
Yeah.
So I'm minusing 4 volts from that. Don't have enough space here, should have written that at the bottom. And now, I got to travel through that resistor. That resistor is a 4 ohm resistor. So I'm minusing 4I.
And then another 7.
And then I'm minusing 7I. And all that has to be equal to 0, because now I'm back to where I started. So now, 12 minus 4 is?
8.
Okay, we're on. And now let's count all our i's. We have negative 2, minus 3 more is negative 5, minus 4 more is negative 9, minus 7 more is negative 16. Minus 16i is equal to 0. Or in other words, I is equal to?
1/2.
1/2. So a 1/2 amp is the current flowing through the circuit. Good? Okay, now, what is the power output of this battery?
10. Sorry.
It's 6.
4.
6 watts. The voltage times the current
Oh.
is how we get power.
Sorry, I was trying to take account of the resistor.
Oh, so we're not going to talk about the net once you talk about its internal resistance. Just the EMF part of the battery. That's what we're specifying.
Oh.
For the EMF part of the battery, how much power is coming out?
6.
6 amps, or 6 watts. So the power, I'll do P sub 1 to let you know it's corresponding to EMF 1, is equal to 6 watts. For the battery down here,
You'd lose 2 watts.
is that what we lose?
Yes.
So for P2 down here, that is going to be minus 2 watts, is its power output. Or in other words, it is absorbing 2 joules per second of energy. That's how quickly it's charging.
Okay.
Good?
Can you remind me what joules are again? There are unit of work, but what is work in terms of?
Kilograms meters per second squared, if you want it that way.
Oh,
Work,
it's
force times distance.
Oh, sorry. I'm just trying to get some intuition.
Yeah. There's a reason you should do it twice. Now let's just calculate the power from everything else, just to see that all our power is being canceled out. So we have 6 watts being produced by our EMF. This resistor is eating up 1 of those watts. So there's -1. This one's eating up 1.5.
So 3.5.
So far we've lost 2.5 watts.
Yeah.
This resistor is eating up 3.5. Am I doing that right? Make sure I am thinking about each of these correctly.
The voltage changes per resistor, doesn't it? So you can't calculate power quite simply. So when you go through one resistor, the voltage will change the next one, right?
Let me make sure I'm not messing up this problem. What example is it?
26.3.
26.3. That was the light bulb one. And on that, we're on the recharging battery one. Okay, 6 watts and -2 watts. Is that what we had?
Yeah.
Okay, 6 watts and -2 watts. Now, when I look at the power dissipating here, I should get -1 watt, right? I should get -1 from that. If I were to do all the resistors, that would give me -8.
How do you know you can
I feel like I'm missing something.
How do you know if you can handle the resistors by 1/2? Because doesn't the voltage change as you go through the circuit?
Is there an E3?
The voltage across each of these is going to be its current times its resistance. It's the same current flowing through this whole thing. It has to be the same current.
But you lose potential as you go through the resistors, so you can't calculate power. Both I think about it wrong. But as you go through the resistor, then you lose potential.
I am missing something obvious here. What am I missing?
Is the problem given?
Huh?
Is the problem given?
Let's see. All 4 resistors is 4 watts. Dissipated in all 4 resistors is 4 watts, not 8 watts.
Yeah, but that checks out. Well, for the
Why is it 4 watts in all resistors, not 8 watts? The total resistance throughout the entire circuit is 16, right? Yeah, missing something obvious. By applying the expression to each of the 4 resistors in that figure, you can show that the total power dissipated in all 4 resistors is 4 watts.
You get number wrong. What are your resistors?
Because I'm being stupid and calculating the potential instead of the power. Let's do it once again. We were doing it right for the batteries, but not for the resistors. Okay, I was treating that like a potential. 2 times the current. So let's calculate the power for just this resistor. So I do resistance times current gives me the voltage. So the voltage is 1. Now I'll multiply by the current again to give me the power, which is 1/2. So I'll take the total resistance times the current to get the voltage across all the resistors, times the current again to get the power.
Right.
And so that's where you get the -4. Okay, now everything is same again. The battery is producing 6 watts of energy. 4 watts are being eaten up in heating up the different resistors, and 2 watts is going into charging the battery. Okay, I know I was missing something stupid. There's a stupid thing I was missing. Everything has to make sense in the end.
Sweet.
All right, that makes sense?
Yep.
Sorry, probably confused you in that little roundabout. Okay, let's do another one. It's been too long since I've done all these, so I haven't solved a problem like this in like 10 years. All right, let's find the EMF, the internal resistance of our battery, that's what little r means, and I for this circuit. So let's see, in this circuit, we have a 12-volt battery here with an internal resistance of little r. We have an unknown battery here. We don't know what its EMF is, but its internal resistance is 1. And then we have a resistor over here of 3 ohms. And the problem told us that 2 amps of current are flowing through here, and 1 amp of current is flowing through here. So first off, what is the I? How much current is flowing through this one?
Why would any current flow through the resistor? Why wouldn't it just stay in that loop on the batteries? Why would an electron physically, like, why wouldn't it just take Short's path and stay in a loop and not?
The majority are going to take the path of least resistance, but they'll still split up and take both paths. So going back to when we did our resistors in parallel, just because this resistor is way more than this resistor, doesn't mean that no electrons will take that path. If this resistor is 10 times as much as this resistor, then 1/10 of the current will take this path as takes this path, because it's more congested, if you want intuition for it. So yeah, current will still take both paths. Okay, anyways, so I know 2 amps flowing through this wire. I know 1 amp flowing through this wire. How many amps are flowing through this wire?
3.
Just has to be 3 amps. If I have 1 amp coming along here and 2 amps coming along here, 1 and 2 coming in must have 3 going out because Kirchhoff's first junction rule. So I here has to be equal to 3 amps. Okay, so we got one of our variables. Okay, now, what should we find next? Little r or our EMF?
It's a little R.
Let's do little r. So little r, we need to pick a loop to walk around. Now, if we choose this loop to walk around, then we're going to be using a loop that reintroduces our variable. Reintroduces another variable. So I'm going to walk this loop. I'm going to start here. I'm going to walk around and come back to there, walking as a little electron. There I go. If I walk that loop, what was my total change in potential?
0.
0. So let's look at our potential. Going from here through the resistor, what's my potential? Going through this resistor here,
It's that minus.
-3.
it's -3 times little r, whatever that little r is. That's what we're looking to solve for.
Yeah.
All right, as I go through the battery's giving me a nice boost. That was a plus 12 volts, right? And now we got, not 9, that's a variable. -3R. Current times R gives us the voltage.
Yep.
Okay, now we're going along. What's our change in potential across here? 2 amps,
6.
3 ohms, we lost 6 volts.
Yep.
And now I'm going along and I got back to where I started, so this all has to be equal to 0. 12 minus 6 is 6, so I'll leave that on this side, is equal to, move that to the other side. Right. So little r now we know is equal to 2 ohms. Okay, now we need to find the EMF there. It doesn't matter which loop we choose to do with this one, because now we have all our other variables figured out.
Yep.
So I'll just start here, and this time I'll go in which direction? I need to do an example where I actually fight the resistor, so let's actually do this way. Do. I think that will be the weirdest way to give you a better example of the weirdness. Okay, so I'm starting here and I'm going to go across that battery.
Yep.
I'm fighting the battery.
You are.
Yeah, the battery wants to boost you this way. I'm fighting the battery.
Yep.
So that's going to be negative. negative our EMF.
Yeah.
Okay, that got me across there.
Yep.
Now, my potential difference going from here to here is actually going to increase because it decreases in the direction of the current.
Right.
So this is actually going to be plus 1 times 1 is 1 for the voltage across there.
How is that possible? Because the resistance is sort of resisting the same, isn't it?
Think about it, if this were a river flowing, are you higher on this end of the river or this end of the river? If the river's flowing that way.
On the bottom one?
This one you're higher, this one has more potential. So the current loses energy going this way, loses potential going that way, so if you're fighting it, you're gaining potential.
So you have to do work to put it there.
Well, we're just gonna pretend we move something around here, and when it's all said and done, our total change in energy is 0. But yes, we did have to, that's what the positive sign here is saying, is that one took work.
Okay. That's weird.
And that's why I wanted to go this way. So if you're going with the current, then you lose potential at the resistor. If you're fighting the current, you gain potential at the resistor.
That makes sense.
Okay, so now we're going this way, and we decide we're going to go in this loop. So now I'm coming along here. Now I'm going with the flow. So that's going to be -6. And that is now equal to 0.
Yeah, okay.
With me?
So it's equal to -5.
And so,
Or just 5. Wait, what? No, it should be -5, right?
The minus is confusing. E is 5.
E would be 5. Let's see. Am I supposed to just do it like that for an EMF period? I think I'm not supposed to assume an orientation for the EMF. Oh, because we're solving for it. I should have left it just as a variable and not put a sign on it. Because it can come out a negative number.
Yeah, it's kind of 5.
So, yeah, so your EMF now is going to come out to -5.
Yeah.
And what is that telling you? We wanted to put a sign on it because we knew that we were fighting it. But what that's telling you is you're charging the battery once again.
Well, you had to put a sign on it in order to get -5, didn't you?
No, I should have just left that as a variable. Whatever your EMF is here, and then let the algebra tell us that it's -5.
But if you solve it how it is right now without the sign, then your E would be 5.
How do you get
Because
negative?
1 is you get E plus -5, or E minus 5 equals 0, so you move the 5 over and you get E equals 5. So you have to have the sign in order to have the -5.
You actually have a point. That is aligned with the way the current's flowing. Maybe I drew it wrong.
Is there an issue with having the negative with the? Oh, I guess there.
How do you get negative 5?
But shouldn't it be
Let's see.
No, because the EMF is in the direction of the current, isn't it? From negative to positive. So wouldn't it make sense to say negative?
We should have left that negative. Let me think. I don't like that switch. Okay, you're fighting the EMF to get there.
Mm-hmm.
You have 1 to get there. You lose 6 to get there.
Mm-hmm.
Oh, now EMF is -5.
Yeah.
There we go. Okay, I was being dumb.
So you
That's what happens when you're thinking about what you know the answer is rather than what it actually is. There we go. Now your EMF is 5. So yes, we were right to assume the sign because we're fighting it,
Which makes sense.
which makes more sense. Okay, initially did it right, knew that we should have gotten negative, and so rationalized a bad decision. Good, we're going through these examples.
Algebra, sorry.
We haven't even gotten to the ugly algebra. Okay. On to the next example. Oh, let's leave that in view a little bit because actually the next example just wanted us to find the power output now for each of the batteries from the previous example. So what is the power output from this battery?
24.
The current, what's the current right there? 3 amps?
The current there is 3 amps.
So it's
Oh, 6.
3 times 12.
Which is 36 watts for that one.
Yeah, right.
Okay, and now, what is our current, or what's our power output for this battery?
-5.
-5.
Okay.
which is what's now telling us that the battery is being charged.
That's a weird.
Let me once again confirm. Oh, they also found the resistance of each of the batteries, but yes, -5 and 36. Okay. And they also want the net power output of each of them. So let's find the net power output now of this battery, which means take into account its internal resistance. So it's putting out 36 watts, but how much are being wasted just heating up the battery internally?
6. It's either 6 or 2.
36. No, I can't be right.
Just 30, right?
1.5.
It's just, the net is 30 watts. You're overthinking it. The resistor is 2 ohms, 3 amps going through it. Internal resistance, 6. Or internal power.
6.
Oh, wait. Did it again. 6 just gets me
The voltage?
the voltage.
Yeah, that's what I thought.
Multiplied by the current again, let's not make this mistake again,
It's 18.
gets us 18, and so the net power output is 18. So actually half the energy of the battery is just going into heating itself up.
Yeah, we should overthink it.
Okay, and now, once again, what's the net power outage output of that battery?
-5.
We have -5 from it, but then there's also energy going into just heating up the battery. How much energy goes into just heating up this battery?
1 watt.
5.
It's 1/3 of it.
How much goes to that resistor?
You have 1 amp flowing through it.
1 times 1 gets us a voltage of 1, times 1 again still gets us 1. So it's going to be a total of -6 watts, I guess I'll call it, being eaten up by it. So 6 watts are going into the battery, only 5 of those watts are actually recharging the battery. The other watt is just
Heating it up?
heating it up.
Okay.
So that's what you typically think of as heat, and that's why I said in physics 1 a bunch of times, what's heat's like the wasted energy. It's always how we think about it. Wasted energy, heat. That's where it all goes. Okay, now let's play the game in a bit more complex way. So now we got this circuit here. Ignore all the currents I have labeled on here,
Okay.
because that's not part of the initial problem. So they just give us this circuit with all these resistors all labeled. 1 ohm resistor, 1 ohm resistor, 1 ohm resistor, 1 ohm resistor, 2 ohm resistor. Good? Our job was to find the current through every resistor and then find an equivalent resistor to all these resistors.
Including the middle one?
Yeah, to the whole scenario. Now first off, let's try and find the equivalent resistor. Let's see, so we've got these two in parallel. But are they really in parallel? Because they're actually not going to the same spot. Parallel means that they start and end in the same spot. So it's like this path is in parallel with this path,
They're series. They're series.
but those two then are kind of series. But then this path, those are in series but parallel with that path. How do you think about this thing? It hurts.
Start with the junctions.
And so we'll come up with a completely different way of finding the equivalence, and we'll put a pin in that. And instead we'll find the current through everything.
Weird.
Okay, now I just arbitrarily chose. Here's my battery. I know it's a 13-volt battery. That's the other thing we know. I arbitrarily choose that I'm going to call however much current is flowing through this wire I1. Completely random.
Yep.
Or completely arbitrary, I should say. I'm going to call however much current is flowing through this wire I2. Now, I'm also going to have some current flowing through this wire, which I'm calling I3. This one is pretty obvious that the current's flowing that way. This one's pretty obvious the current's flowing that way. This one, I have no clue which way that current's flowing. I'm just calling it that way.
Doesn't really matter, does it?
If I got it wrong, then I3, when I calculate it, will come out a negative number, which will mean my current was actually opposite to the way I assumed. So you just label your current however you want, but you only want to put as many variables on there as you need.
Yeah.
So now that I've labeled this current, and this current, I can now relabel all the currents through all the other wires in terms of those variables. So I want to limit how many variables I actually need for my current. So now, if this is I1, and we have I3 flowing that way, then down here we have I1 minus I3. I1 came in, I3 went that way, so I1 minus I3 must be flowing that way, just using the junction rule. So we look at that junction to figure out that. Looking at this junction, I have I2 flowing in and I3 flowing in, so I have I2 plus I3 flowing out. What do I have flowing out right here? Well, I have I1 minus I3 flowing in and I2 plus I3 flowing in, so I have I1 plus I2 flowing out, which is obviously what's also flowing in back up at the top.
There's an I, right? Just your total current.
Sorry, what?
Just your total current. Should be
Sure, but wow, limit our variables as much as we can. So now I have 3 variables. Now, since I have 3 variables I'm solving for, I need to come up with 3 equations. So I need to pick 3 loops and calculate the voltage across each of those loops and write down each of those equations. So my first one, I'm going to start right here, and I'm going to go in this loop. Do. With me?
Yep.
So coming here, nothing. Oh, sorry, I'll start right here actually is where I started. So starting here, first we get positive 13.
Yep.
Then minus the voltage coming across this resistor. So that's I1 times 1. Then minus the voltage coming across this resistor. What's the voltage across this resistor? It's the current times 1. And now I'm back to where I started, so that all has to be equal to 0. Now, pick a different loop, and you'll get a different equation. So now I'm going to start right here. This time I'm going to do the complete outer one. You with me? So doing the outer one, crossing the battery gets us 13. Crossing here gets us current times resistance, and we subtract it. Once again, subtract current times resistance for this one. And then we're back to where we started, so it's equal to 0. And then for this last one, try and remember which one I did here. I think I'm doing this right here.
Oh.
So starting right here, I'm going this way, which is negative I2 times 1. Now notice this way I'm fighting the current. So I'm going to get plus I3 times 1. And then this way I'm fighting the current. So I'm going to get I1 times 1. Oops, forgot to write my times 1. Equals 0. And there we go. I now have 3 equations with 3 unknowns. And it's just standard algebra that you know and love.
Do you have to write out every loop if that's possible, or just?
No, you just need as many, because there's other loops I could have used. I didn't use this loop. I didn't use this loop. There's other loops. I just need as many loops to get 3 equations for my 3 unknowns. Now, because the i's can be a bit messy for your brain, I'm just going to replace all my I1s with X, all my I2s with Y, and all my I3s with Z. I'm going to rewrite each of these equations. So we have 13. How many I1s did we have? We have minus 1 and then minus another one for a total of minus 2 I1s, which I'm calling X. And then we had a minus I3, which is a plus I3 or a Z.
Yep.
Same thing down here. Here's our 13. We have a negative I2 and a negative I2 for negative 2 I2s, which is what we're calling Y. And then we have minus an I3 or minus a Z. Down here, minus I2 is minus Y. Plus I3 is plus Z. Plus I1 is plus X. And now, here's our 3 equations with 3 unknowns. And you just solve it exactly the way you know and love from your algebra days. So, pick one. Then we're going to substitute it to the other 2. Doesn't matter which one we use.
Use the bottom one substitute.
Yeah, that works. Okay, so I'm going to take the bottom one here, and may as well solve for y. So from our bottom equation here, I get that y is equal to,
Z equals X.
and I'm going to write as x plus z just for the sake of alphabetical order. Okay. Now, substitute that into here
Yep.
to get z in terms of x. So rewriting this equation, making this substitution. I'm going to get 13 minus 2y minus z equals 0. we have minus 2, I'm going to rewrite it one more time, we have 13 minus 2x, and then we are subtracting a total of 3z.
Yep.
Now I'll just solve for what minus 2x is, because this was this equation, right? I'll just solve for whatever minus 2x is, because I have a minus 2x in there that I can substitute into. So using, oh sorry, this is equal to 0. So what is minus 2x equal to?
3z plus, or minus 13.
3z minus 13. Okay, now I'll substitute that into the top equation. Top equation becomes 13 minus 2x. Minus 2x, we just really found out, is the same thing as 3z minus 13. Uh-oh.
What? What's,
What did I do weird?
you didn't?
No, I did something weird, because 13 and 13 is going to be 0, and I'm going to get 4z equals 0, z equals 0. Z's not 0.
That is good.
Oh, sugar.
Did we drop a sign something?
This is why you solve these things using matrices, which
Yeah.
you'll learn how to do in linear algebra. But there's a lot of mistakes I could have made. It could be all the way back to just setting up the problem. Let's see. Hopefully I followed similar to the author's way. 13 minus I1. One way to solve these simultaneously equations is to solve, okay, let's see, for number 3. Check on those equations to see if I have it. 13 minus 2x plus z equals 0.
Okay.
That's good. Let's try this one. Negative 2y. Oh, 2 there. That's a 2.
So that should be 2i.
So this was this equation.
Okay. That makes sense.
All right. I even tried writing that down ahead of time so I wouldn't make a mistake like that, and still made the stupid mistake. Okay, so that will make this junk. Okay, let's see, and we'll rewrite out this equation. Lots of room for algebra mistakes. Okay, we still have our 13. Let's see, we have negative y and negative 2y for a total of negative 3y. And we have negative 2z. Did we do that right? I think we did it right. Okay, this equation, we can still solve for y, that's fine. Substitute y into, doesn't matter which of these, I'll substitute into this. So substituting into there, we get 13 minus 3y, I'm just going to write it as minus 3x minus 3z, minus 3y minus 2z is equal to 0. Is that going to simplify very nicely? Not particularly, huh? Oh well. So what do we get from that? We get 13 minus 3x minus 5z is equal to 0. Did I do that right? Make sure we're not making any mistakes.
Sure, there's one.
And then, well, we'll solve for the z, I guess.
It's all right.
I don't like how fractions are coming out of this. Makes me think I'm making a mistake again. Because I'm going to move the 5z over there, divided by 5. I'm going to get z is equal to 13/5 minus 3/5 x. Which I don't like.
Yes.
But we'll see what happens. So I got 13 now minus 2x plus z. So So plus 13/5 minus 3/5 x equals 0, right? Multiply both sides by 5. 13 times 5 is 65 minus 10x plus 13 minus 3x equals 0. 65 plus 13 is going to be 78.
Yeah.
So we got 78 is equal to, move all my x's to the other side, gives me 13 x's, which gives me x is equal to 6. Okay, came out nice.
Then we substitute back in.
Okay, so we know our x. Woohoo! So x, which was I1, we know is 6 amps. So I1 is 6 amps.
Fun.
Okay, now that we know x, we can easily find,
One.
I think z, right? We have z in terms of x, right here.
Yeah.
So, we have
33/5.
3 times 33.
Oh, man. Well,
So 3 times 6 is 18.
yeah.
18 plus,
This is
that
31.
seems wrong.
31/5.
There's no way that's the answer for z. All right, let's start by I1, see if he got 6 amps. I1, he got 6 amps. I2, he got, where did he put I2? I2, he got 5 amps.
X is 6. 6. Oh, it's minus 13/5 minus.
Oh, minus a duh. Thank you. All right, we'll look at this one. Probably easier to think about. Well, put the 5z over there, but 13 minus 18 is
Negative 5.
-5. So z is
Well,
1. Oh, wait, no, -1. What do we use z for? I3. I3 is -1,
but if we just change the direction, it's 1, right?
which means it's 1 amp in that direction. So I intentionally did it in the wrong direction on one of them. Okay, and now I2 is equal to, we can use this one. Add them together, so it's equal to 5 amps. Okay, and there's our different currents. And so now I can find the current through each of these resistors. Through this resistor, 6 amps. Through this resistor, 5 amps. Through this resistor, 1 amp. In this direction, but 1 amp. Through this resistor, 6. Through this resistor, 7, right?
Yeah.
And then our total current, if we want to call it that, I1 plus I2. What's our current through this part right here? 11 amps. And so now our $1 million question, what resistor would I need to replace this whole mess with to get something equivalent? So that would be 13 volts and 11 amps. So what would R equal? Just using Ohm's law,
13/11s.
it would be 13/11s.
Weird. Cool.
Okay, which is not something that you want to try to reason out from that mess. That'd be a nightmare. All right, so there we go. There's messy algebra. Now, the fun stuff, but calculus stuff. So hard part of the lecture now. There was the easy part, just doing algebra. Easy part, that's full of mistakes. Okay, RC circuits. What is an RC circuit? It's a circuit that has a resistor and a capacitor. That's an RC circuit. So here I have here's my circuit. This is going to be a switch. So it's going to close this way and then close that way. I'm just drawing two circuits in one. So the first scenario we're going to consider when the switch is closed right here. So our circuit is this. So it's going to have a battery, a resistor, and a capacitor. Current flowing around like this. With me so far? Now, what's going to happen is, initially, as we close this circuit, right? So I have this all set up. I have my battery, my capacitor is initially not charged. If I close the circuit this way, then now what that's going to allow is my capacitor to start charging. You see that? And then, when I flip my switch now, then it's going to be like this middle part doesn't exist, and my current's going to flow like this, and now my capacitor is going to discharge. So I drew it this way so you can see charging the capacitor, and then discharging it. Charging it up, and then discharging it.
What is it? Oh, I see it.
So when I'm saying that we switch it, now it looks like that. And so now whatever current is on the capacitor, whatever charge is on the capacitor is going to flow off and go through here. What's a concrete example of where you might see a circuit similar to this? Ooh, where's my camera? Oh, we already moved it for all this. A pacemaker. A pacemaker is an example of where you see something like this, where this resistor down here represents your heart. And then this is an actual resistor inside the pacemaker component. And so what happens is, the switch is this way, it's on some sort of timer. It's this way charging up the capacitor, and then it flips, letting the current go down and shock your heart. And then it closes, charges up the capacitor, and flips. And goes down, lets it shock your heart. That's ultimately what makes your heart contract, is sending an electric pulse down it. And so a pacemaker triggers the beating of your heart for you at a particular pace that is dictated by the circuit. So there's an example of where we would actually use these RC circuits. So we're going to come up with the math for figuring out how quickly a capacitor charges up, and then how quickly a capacitor discharges. So first we're looking at this case, charging it up. So ignore the bottom part of the picture. You with me?
Yeah.
Okay. Now, initially, what is the charge on the capacitor when we first close this up? 0. There is no charge on the capacitor, right? And as time goes on, we're going to start building up charge on the capacitor. So there's initially going to be a current of charge flowing on the capacitor. As more and more charge builds up on the capacitor, is it easier or harder to get more charge on the capacitor? It's going to get harder and harder, and so the current's going to slow down and slow down and slow down. So we're going to start with some initial current. That's going to get lower and lower and lower as our charge on our capacitor gets higher and higher and higher to some maximum charge. You with me?
Yeah.
Okay, now doing what we already did a million times in this, I'm just going to look at taking a loop around this thing, look at the voltage. So, starting here, we go through our battery, our EMF, then we're going to minus, or I'll just say that our EMF is equal to the potential difference across here plus the potential difference across here, if you're good with it that way.
Okay.
So the EMF is equal to, what's my potential difference across a capacitor with capacitance C?
It's the charge over C.
It's going to be our charge over C. And then, what is our potential difference going to be across our resistor? Ohm's law is just going to be
The current times.
I times R. Now, in this scenario, Q and I are variables. They are changing. Initially, what's my charge?
0.
0. So maybe scribble some of this down really quick. Q naught, meaning our initial charge, is equal to 0. What's our initial current?
I. Right.
Our initial current, let's really quick solve this for the current. Solve this equation for the current. So I'm going to move this term to the other side and then divide by R. Maybe I'll do it one step at a time. So I times R is equal to our EMF minus Q over C. Divide both sides by R, and that gives me that I is equal to 0. It's going to be equal to our EMF over R minus Q over R times C. Right?
Yeah.
Now, in the beginning, what is our initial charge?
0.
0. So what is our initial current if our charge is 0?
It's just E over R.
It's just E over R.
Oh, okay.
So initially, from the current's perspective, it doesn't really know about the capacitor stopping it from moving until some charge builds up on the capacitor.
Right.
So initially, it's just flowing with its maximum initial current, the EMF over R. So there is our current. Now, I'm trying to come up with a function that will tell me what the charge is at any given time and what the current is at any given time. Now, here's where, before I do that, I'm going to rewrite this one more way. I'm going to multiply this one top and bottom by C, and then factor out the 1 over RC. So current, I'm also going to write current funny. How do you spell current? The derivative of charge with respect to time is equal to, I'm going to pull out the 1 over RC, and then inside we have our EMF times C minus Q. So I multiplied this one top and bottom by C so I can factor out the 1 over RC for both of them. And then our current is our derivative of charge with respect to time. Now, why can I say my current is a derivative of charge with respect to time? Because my current is quite literally the change in charge on my capacitor. That's where the entire current is going to. So in this case, the current is directly related to the charge on this plate in this way. Good? Now, last thing to notice, we'll say it here in a second. Should we say it now? We'll say it now. When it's fully charged up, I'll say it in the end. We'll say it in the end. Sorry. Keep going with our thought here. Okay, so here is our change in charge with respect to time. And now, notice that we have a dq here and a q over here. So obviously this is a differential equation, which you can clearly see. So,
Is this a separable differential equation?
yep, so we got the dq over the, I'm going to move this over here.
Oh.
And I'm going to multiply both sides by negative because we never like our variable to be negative. So I'm going to put this as Q minus our EMF times C is equal to, and to account for that, I'm going to put the negative sign on this side.
Right.
Negative dt over R times C.
Yeah.
Good?
Yep.
And now, what do?
Yeah, great.
We integrate both sides. So as our time goes, we're going to call time 0 when we initially close that switch and charge starts flowing. That's our time 0. So this, we integrate from time 0 to time whatever t we want to know the charge at. And our charge is going to go from 0, there was initially no charge, but then q is what we mean by the charge at time t. Q is a variable changing with respect to time.
I thought they had the same integration now.
They are.
They are.
As t goes from 0 to t, our charge goes from 0 to q.
Oh, obviously. Okay.
It's just what we mean by just making that clear. Okay, so now taking this integral, notice that we have the variable downstairs, so this gives us a
Minus 2. And yes, what?
the integral of 1 over x dx.
Oh, natural log of x.
There you go, natural log of x.
Yeah.
Let's move this. I know I have scribble room on the whiteboard.
Okay.
Okay, so not sure what I brought there. Okay, so here we have natural log of Q minus our EMF times C, right?
Minus.
Well, evaluated from, I didn't do my evaluation yet. Let's go ahead and do the evaluation in one go. So this is what you get when you plug in Q for Q, minus what you get when you plug in 0 for Q, minus the natural log of negative our EMF times C.
And you can do like a little trick with that.
Yeah, the log, the difference of the logs is the log of the quotient.
Yes.
So we'll do that substitution, but before we do that, let's really quick do this. This is equal to our integral over here. That's easy. All that's just a constant, just a dt, which leaves us with just t. So this is equal to negative t over r times c. Good? Now, exactly what you said. This is taking a lot more space than I thought. We'll have to do the discharge somewhere else. Okay, so the log, the difference of a log is the log of the quotients. So natural log of Q minus our EMF times C all over negative our EMF times C is equal to negative T over R times C, right? Raise both sides to the power of E, an exponential undoes a logarithm. So E to this power is just equal to Q minus our EMF times C over negative EMF times C is equal to E to the negative T over R times C, right?
There's no way we can factor out the E times C.
Now, we're going to multiply both sides by negative E times C, and then add that E times C over there. See if you can follow all this. So Q is going to be equal to E times C, that's this one, minus, when I multiply this over to that, E times C times E to the negative T over R times C. With me? Now I can factor out that E times C to both those. But before I do that, now let's make one final note. Coming back, I'll let those G's confuse you as part of this equation. Coming all the way back from the beginning, when our plate is fully charged, what's our current? Zero. So our current is 0 at our final state. So our final charge is just going to be our EMF times C. So EMF times C is just our final charge. So Q here is equal to, I'm going to replace those, factor them out, but I'm going to replace with Q sub F for our final charge, times 1 minus E to the negative T over RC. Okay, and so what is this equation telling us? My charge at any given moment is going to be some portion of my final charge. Now notice, as T gets bigger, then E is to a bigger negative exponent. So the value of E here gets smaller. So 1 minus E is becoming a bigger number. And so our charge gets bigger as time goes on. What's our initial charge at time 0? How much charge is on this plate right when I flip the switch? 0. And let's see that in here. 0 divided by anything is 0. E to the 0 is 1. 1 minus 1 is 0. So our initial charge is 0.
But doesn't that mean that you'll never reach a current?
It means that you never quite reach your final one. And it's always drifting on more and more, and so it has an asymptote. But it gets really close. Okay, now there is our charge on our capacitor at any given time. How do we find our current at any given time? Because our current is also changing with time.
It's just the derivative of time.
Perfect. And so all we have to do is take the derivative of this. Probably easier to do it from up here. What's the derivative of a constant?
It's just
0. What's the derivative of an exponential?
Just the exponential.
Just the exponential, but now we have to do the chain rule. So multiply by the derivative up there, which is just, remember t is your variable, so it's just negative 1 over RC. So our charge now is equal to negative 1 over RC from my chain rule times negative times just this thing right here.
Okay.
But that Q times C is what we mean by Q sub F. Maybe I'll just keep writing it.
This should be negative Q sub F, though, shouldn't it?
Yeah, so it's going to come out positive. Negative our EMF times C times E to the negative T over R times C. Okay, so there's our current. Negative times the negative is positive. Notice that top and bottom, the C's go out. And so we're left with our EMF divided by R, which is our initial current.
Oh, yeah.
And so this whole thing simplifies to just our initial current, times E to the negative T over RC. Nice and elegant.
Cool.
And now, what is this saying? What is our current at any given time? This is saying our current now is getting smaller and smaller as T goes forward. As T becomes bigger, E is to a bigger exponent, so E is a smaller number. So we're taking I and multiplying it by a smaller number. Now, not obvious from the units, but if you were to take the units of resistance, ohms, and you were to multiply that by the units of capacitance, farads, then the result would be seconds. And you can go do that exercise yourself if you want to go work through all the units.
That's good.
I think it's worth writing them all out and canceling a bunch of stuff. In other words, a resistance times a capacitance gives you a time.
Okay. That's so.
And so for every RC circuit, the actual R times C, sometimes represented with a tau, they call the time constant for that circuit.
And it's the time to get to fully charged or what?
Now, let's see what it is. So when I plug in, looking at this equation for my charge, when I plug in RC for my time, then RC over RC is just 1. And so it's E to the negative 1. So it's 1 minus 1 over E. 1 over E, I can't remember, something like 30.32. So minus 1 minus 32. It's telling you when it reaches 68% of its charge.
68.
Roughly. Probably 65, probably 64.
That's such a random constant.
But at the same time, it tells you when the current is then at whatever the reciprocal is, 32% of its current. Let's pretend I'm remembering right, and it's 0.32. So it's when the current is at 32% of its value, and the capacitor is at 68% of its charge. Now, come back to our example of pacemaker. What would you want then? So if you wanted your switch to go off after RC seconds, you would use a capacitor there that then stores 68% of the charge that you wanted to be shoved onto that heart. Because you knew that's how much it would have charged up in RC seconds. Because it's not obvious to say, when you have that on there, when should we flip the switch? When is it charged enough? Do we just wait forever and wait till it's completely, really close to fully charged? What do we do here? You see the problem? Because the charge is constantly changing.
Yeah.
And so we got to come up with some time where the charge will be at some value that we know. Now, I don't know if they actually do this in a pacemaker. I'm just giving you the theory for how you could design one yourself. So there we go. There's charging up a capacitor on an RC circuit. Here's the current at any given time. Here's the charge at any given time. Now, what we're going to do next, lucky you, is do it for discharging.
Okay.
So let's work through this again for discharging. I'll just move this over and scribble out some space so we're not as cramped. Go ahead.
How rude.
Okay, so for this next one, we're assuming that the capacitor is already now charged up. So we're going to say that our capacitor, Q naught, is some value, some initial value. And that's going to be at time 0. Time 0 now means when we flip the switch and now we're letting the current off. That R could be a different resistor from what we talked about before, but who cares? So now when you flip that switch, your circuit now only has a capacitor and a resistor. There's no longer a battery involved.
Yeah.
Okay, so it has some initial charge Q naught, and if we're tracking the voltages, the voltage across the capacitor, which is Q over C, where Q is always changing, plus the voltage across our resistor, which is I times R, now has to be equal to 0, not the EMF. There's no EMF in there. So I go in a loop around this one. So we're throwing our switch now. Throw the switch. So here's our circuit. Ignore the middle part. If I do a loop around the circuit, those are my changes in potential, and it should be 0. I'm going to do exactly what I did before, solve for I. So I is equal to Q over RC. I'll go a little bit faster on this one now since it's pretty much the same thing. So dq dt is equal to Q over RC, which gives me that dq over Q is equal to dt over RC. Integrate both sides. We're integrating. Now our Q this time started at Q naught and went to Q at some times t. And our dt here is still at time 0 to time t. Where time 0 is when we flip the switch. So a little bit different on our bounds of integration here. So for this one, we're going to end up getting the natural log of Q over Q naught is equal to T over R times C. I'm a little concerned that I don't have a negative sign. And it's because I'm stupid on my algebra. When I move this to the other side, we got a negative sign. Which gave me a negative sign, which gave me a negative sign, which gave me a negative sign. Okay. There goes the stupidity. Now, e to the both sides. So over here, we get Q over Q naught is equal to e to the negative T over RC. Once again, you see, same exponential that we had before, which is why I knew that there should be a negative sign. Solving for Q now, pretty straightforward. Q is equal to Q naught times e to the negative T over R times C. So that gives us our charge at any given time. And now, our charge is just decreasing as time goes forward, getting less and less and less.
So it's the same as our current, the I switched the first one.
Kind of, very similar to what our current was doing on the first one. Now let's find our current on this one. Really quick, what's our initial current?
It's 0. Wait. It's really close to 0.
Our initial current, I naught, no, it's going to be at its biggest value. The current is going to be leaving at its maximum value. But first off, notice what our current is initially. It's just negative Q naught over R times C. Why is our current negative?
It's flowing out.
Because it's leaving the capacitor. We're talking about the charge on the capacitor. And so if we're going to think about our current as our change in charge with respect to time on our capacitor, it better be negative. The current's leaving the capacitor now, not moving on it. Okay, so there's our initial charge. But now, really quick, let's calculate, not our initial charge, our initial current. And now let's really quick calculate our current from this by taking the derivative. And so the derivative with respect to time of Q is equal to I. Derivative here, once again, derivative of an exponential, just the same thing, but chain rule. So I'm going to bring down the negative RC, or the negative 1 over RC. So I get negative Q naught over RC times e to the negative T over R times C. Once again, that is exactly our initial current. And so this comes out, once again, to exactly that times e to the negative T over RC. And so it's identical to what it was here. If you have the exact same resistors in both scenarios and the same capacitor, then the rate at which the charge flowed onto the capacitor is the exact same as the rate at which it flows off of the capacitor. Okay, so now let's briefly talk about circuits in a house. So there goes the hard algebra or calculus stuff. No more calculus stuff. The rest of this just feel good stuff. Trying to give you some intuition for the stuff you see around you. And then maybe talk about batteries. So looking at your house, the big M here stands for your, now I lost it. Thank you, the meter, where it feeds in. On your meter, I'm going to represent everything with direct current. Your house does not actually use direct current, it uses alternating current. So I think we'll come back and give you a more accurate picture of what this looks like later. So this picture's a lie.
How do you even represent alternating current?
When we get there. But, so, we have what we call the hot line coming in, and then the neutral line. We think about the hot line is where the current comes in, and the neutral line is where the current leaves. With alternating current, you actually have two hot lines, one neutral line, but yeah, we'll set that aside. Okay, anyways, so first off, it comes into your house, and your hot line first is going to go through some sort of main fuse, or something that acts logically equivalent to a fuse. Let's briefly talk about how a fuse works. If I have, which of these can actually draw decent? if I have some circuit here, so here's my battery, whatever. We'll say that my battery has an internal resistance. Let's use a car battery. So we'll say that this battery has 12 volts. And then the internal resistance of my battery, for a car battery, that's roughly 1/50th of an ohm. So car batteries, even though a car battery only has 12 volts, like a 12-volt battery, what's so special about a car battery? The special thing about car battery is it has very low internal resistance, and we'll see why this matters. So let's say that your 12-volt battery, whatever it is, it's hooked up to some resistor, blah, blah, blah. Let's make up a resistor for this. We'll just say that it's 12 ohms, just to keep things simple. How much current flows through this circuit? If that's a 12-volt battery, and this is 12 ohms of resistance, and the internal resistance is 1/50th, basically negligible in this scenario, then it's basically 1 amp flowing through here. A little less than 1 amp.
Yeah.
You with me? Now, imagine that some poor soul comes along with a copper wire, purple for copper wire, and they decide to attach this end to this end, so that there's no resistance flowing. And now it just has to overcome the internal resistance. Now what's our current? Well, our voltage will be equal to our current times our resistance. Our resistance internally is just 1/50th. What's 12 times 50?
600.
600. 600 amps would flow through that thing. If you went to your car battery and you took a wrench and you went from the positive terminal to the negative terminal and let flow through there, that is a lot of current, which is all basically going into heating up your car battery, which is going to boil whatever the sulfuric acid or whatever it's using inside of it, which is going to make it leak out. This is very bad for batteries. You should not do this. In this specific case with the car battery, it gets hot enough that you can actually weld the wrench on. And then there is no taking it off, and it's just going to keep going, and you're going to do a lot of damage. In that case, I suggest you get far away from the battery. Not a good thing. That's what we call short-circuiting the circuit. That's what it is.
That makes sense. Cool.
That's a very bad thing. So when you're at your house here, if some poor soul decides to hold the copper wire up and connect the hot line with the neutral line, they're asking to get fried. Because now suddenly a lot of current's going to flow.
Yeah.
And so what a fuse is it's a very delicate wire. If you ever look inside of a fuse, it's just a very thin wire there that if it gets too hot, it just melts. So if too much current flows through it, it's going to heat it up enough that it just melts the wire, and then it can't flow through anymore. So it's a safety feature. That's how a fuse works. So that's what these are going to be. There's going to be like your main fuse, and for each branch in your house, there's going to be a bunch of these. They'll also have their own fuses. You're going to be using breakers, not fuses, but same kind of concept. Can't tell you how they actually work yet, but we'll pretend it's all fuses. If you've ever done like Christmas lights, that's fuses inside the actual Christmas light. Anyways, so you have your hot line now, connects to some outlet, and your neutral line right here. What happens when you plug something in there is you're basically completing the circuit. You have two prongs. One of those prongs is essentially connecting to your hot line, which then goes into your machine, your vacuum or whatever to do some work, and then comes out through the neutral line back into your ground circuit. Now this here means that it's also connected to the ground, meaning it's actually connected to the ground outside.
Why does that matter?
Why does that matter? In normal cases, as much current is coming in as is leaving, and nothing strange is going on. But something might happen, like your house gets struck by lightning, and now it can't handle the load that way, it needs somewhere else to go. Or other weird electrical events can happen. Another thing, this is meant to represent a light switch. Here's your light, here's your switch. You flip the switch, what does it do? It closes the circuit, allows electricity to flow through your light. That's how you get light. You send a bunch of energy through a resistor, a bunch of current through a resistor, that's how you make light. It gets so hot that it starts glowing beyond infrared into visible light spectrum. That's the most dumbed down light bulb. Last thing to talk about now, which I didn't want to draw in here because it makes a mess of it, is your outlets, they also have that third, the mouth, right? You got the two eyes and the mouth.
Yeah.
What does the mouth go to? The mouth goes basically, it's a very conductive copper wire that goes directly to your ground. That's where it leads to. And this is meant to connect to the actual casing of the thing that you have. So it's not connected to the actual circuit, it's connected to the casing of the things. So if I have some metal container that I'm plugging in, the ground wire is that metal container in case the metal container somehow gets some charge on it and sends it to the ground.
How does the charge from the container flow? Is the ground, is there a potential difference between the ground and whatever container that's there?
If a charge is building up on it, yes. Right? If a charge is somehow building up on the container of the thing, and then I come along and touch it, now I'm the path to the ground.
Yeah.
If it already had a better path to the ground, it's not going to bother with me. So say that there is some problem with the device, and for whatever, here's the container of the device connected to the ground, and for whatever reason, your hot wire, which isn't supposed to be doing it, is has some of the coating cut away somewhere. It's like nicking it. And so in that nicking it process, that can make it dangerous. Well, not very dangerous now if it's grounded, because lightning likes, or electricity likes copper a lot more than it likes me. And so it will take that path.
So it's a safety feature.
So it's another safety feature, keeping it grounded from the actual container. The last safety feature, which, I can't talk about because we don't have break. Well, we'll just talk about it even though we don't have it drawn up here. Now I lost a name for it. Bathroom outlets.
GFCIs?
GFCIs, is that the letters?
Ground fault circuit breaker.
Sounds right. Okay, so how do those breakers work? So those breakers, they are hooked up to both a hot, and they're also hooked up to what I use for the neutral. To the neutral. And they actually monitor, have a way of detecting how much current is going out of this one, and how much current is coming back in this one. Because now let's say, even though your device is grounded or whatever, you happen to be not wearing any shoes, big puddle on the floor, now you're holding the thing, and now you're actually a pretty good path for some of that current. Because even if there's a better path, some of it will still choose you, and it can be enough that actually hurts you. And so, if you're over here, how do we draw you? So these are both coming to some device that you're holding. Whatever. Holding some, here's the device you're holding, whatever, here you are. Happy as can be. But you happen to be standing in a puddle. Not smart. Or maybe you're in a tub and you decide to drop your hairdryer in the tub while you're bathing while it's plugged in. Whatever. Something like that.
Yeah.
Crazy scenario, out to kill yourself, best way you can. What would happen is some of the current, rather than coming back through here, would somehow go through you instead and get grounded. And so it's not coming back down here. This detects, I'm sending out more than I'm getting in. Flip. And that's essentially what it does. So another safety feature beyond it being grounded and beyond just fuse type systems.
Is that detection like a computer system, or is that?
No, yeah, I'm not positive. I think it's typically through magnetic fields. So I think we'll come to this. It's been too long. I don't remember is the truth.
Okay.
But I want to say that they use magnetic fields to do the physical detection. And then who knows, because even I can remember, it could be like how it worked initially and things changed, so no idea. Anyways, there's that. Last thing, since we have just a couple minutes, I told you I'd talk to you, that ends the chapter material. But you guys kept asking about batteries. I said I'll try to go over one example of a battery. And I told you it'd just be a crap ton of chemistry, so that's what it's going to be. Okay, so I'm going to be going over with you an alkaline battery. Here's this alkaline battery. The outer shell, which has a positive node here, is composed of, let's see if we can figure out what this is, magnesium dioxide. I think is what that is. So magnesium with 2 oxygen, magnesium dioxide. There is going to be, the inner part, the negative part, is just zinc. There is going to be some barrier, that's what the blue is showing, some barrier there, that both water and, what are these called? Hydroxide, I think? Hydroxide can travel through that barrier.
They can travel through.
they can move through it. So it's a porous barrier that these molecules happen to be able to move through just fine.
So like osmosis.
Sure. And then there's going to be a gel on either side of the barrier, kind of holding everything in place. And that gel is going to be, if I remember hydroxide, then this is going to be potassium hydroxide. And why is it called an alkaline battery? Because potassium hydroxide has a pH of 14. Very alkaline. Acidic, alkaline.
Yeah.
They're opposites of each other. Very low base. Does that make sense so far?
Yeah.
You know the difference between bases and acids? Okay, so good base. Now, what happens to start our reaction? Now, since it's a base, what are bases good at providing? What? Okay, maybe talk about the pH for a second here. What has exactly a pH of 7? Right down in the middle. What?
Water.
Water, pure water. Pure water, pH of 7. Basically, what makes you an acid? An acid, this is a lie, but it's close enough to the truth. An acid means it's easy to get H positive ion off of you.
Okay.
That's what it means. What does it mean to be a base? It's easy to get OH ion off of you with a negative charge. So a positively charged hydrogen, a negatively charged OH group. That's what it means to be a base.
Okay.
The easier it is to get these things off of you, the more of a base you are. The easier it is to get these things off of you, the more of an acid you are. Water, when it goes from H2O to an H plus and an OH minus, it does both of them at the exact same rate.
So it's happening.
It produces the exact same many of these as it produces of these, if it's pure water. And so it's right smack in the middle. It's no better at producing H plus than it is at OH minus.
Makes sense.
Okay, so if this is very basic, very alkaline, which is why it's called an alkaline battery, by the way, I'm not sure if I said that, then it's very good at providing OH ions for people to use. Okay, so kicking off our reaction here, starting here where our electrons are going to flow out. So we've got zinc down here. You with me? So that zinc is going to get 2 OH ions from the potassium hydroxide, if I'm remembering the name.
Okay.
And it's going to combine with it to produce, I'm going to make up names. It's been too long since I did chemistry, like 10 years. Zinc oxide and water.
And 2 free electrons.
And then those 2 free electrons are escaping out through the bottom. So here's where your wire, here's where your wire to the negative terminal of the battery is, and then your circuit comes in like this. With me so far?
Yes.
Okay, so there we go. We got 2 electrons, whoop, and they're eventually going to go around and they're going to come back into the top. So let's capture them now as they come back into the top. Here at the top, we have magnesium dioxide. Now it turns out it's going to take 2 magnesium dioxides to deal with the electrons from the 1 zinc.
Okay.
So 2 magnesium dioxides are going to take, did I tell you that this thing here in the middle, this separator is, think about it as like soaked with water. So there's going to be water sitting in there. It's going to take 2 waters. Now one of the waters could be one of the waters created from our initial reaction. Remember when we did our zinc here, and we converted it into zinc oxide, we also produced water.
Yeah.
So one of those waters makes up this water, but it's also just going to use a water that was already inside the battery. So water is one of the things being used up inside the battery. And those 2 electrons, and it's going to do that.
Okay.
And if you track all the atoms, they all get accounted for. Our 2 magnesium are right there. We have
2 oxygens.
4 oxygen for those 4 oxygen. Those 2 oxygen are right there. 2 of the hydrogens are here. 2 of those hydrogens are here. And both the electrons are now on the OH group.
Okay.
And now that OH group is back with the potassium hydroxide, and it's just back in the gel. So when it was all said and done, what happened? We start out with a zinc atom down here, 2 potassium dioxides, and a water molecule, and ultimately converted it to zinc oxide and 2
Oh, that thing.
magnesium oxyhydroxide something. It's gonna be close to that.
Yeah.
And that's what happened in the process. Those got converted to those. And in that whole process, 2 electrons made their way through the circuit. And as we do this process, more and more of our magnesium dioxide is being converted more and more to our magnesium, whatever, oxy, hydroxide, whatever it's called. And as this is being converted to this, it's using it up.
Yeah.
And we're using up the water inside. Water's going to nothing. I did the empty set to say nothing. It's just flat out being used up. And the zinc is being converted to zinc oxide. And it's just being used up. And as you use that up, the battery is dying. And once that reaction can't really take place anymore, your battery is pretty much dead. And so that is how the battery works. And if it's a rechargeable battery, then you shove the electrons the other way and you reverse these processes, forcing it back to what it was before. Okay, so I told you it's not very satisfying. It's just going to be showing you a bunch of equations and saying, see, atoms, same atoms on both sides.
Yeah.
Trust me. But there we go. There's an alkaline battery, and that's as much as we'll be saying about batteries, I think. Since the book, I don't think, says anything about it. I tried to find it if it does. Maybe it does later, and I just couldn't find it, but I don't think it did.
Okay.
So there's the best I can do for an alkaline battery.
Cool.
And that finishes that chapter. Our next chapter will be on magnetism.
Oh, wow.
Magnetism and the way charges react with magnetic fields are extremely, extremely unintuitive. This is where the crazy unintuitive stuff starts. So I strongly recommend reading the chapter before class. Any other questions you want recorded before we call it a day? All right. Hopefully see you next time. The class keeps growing.